Welcome to part 3 of the Maker Lessons Ohm's Law series on current. Starting this video with the definition of current will allow you to put our analogies and visuals in context as we progress. Current is defined as the flow of electric charge. When using the water tank analogy, current is represented by the flow of water. We could think of the amount of water flowing through the pipe from the tank as current. Here we have two tanks, each with a pipe coming from the bottom. Each tank has the exact same amount of water, but the pipe on one tank is narrower than the pipe on the other. The flow of water from the pipe that is smaller is less because only so much water can pass through any section of the pipe at any one time. The same is true in a wire. Charges fill up the entire cross-sectional area of a conductor and flow through that area. To measure the current of water, we would measure the volume of water flowing through a point in the pipe over a certain period of time. With electricity, we measure the amount of charge flowing through a point in a circuit over a period of time. This amount of charge is referred to as an ampere, the unit for electric current. An ampere is defined as 6.241 times 10 to the 18th power of electrons passing through a point in a circuit every second. Amps are represented in equations by the letter I. The symbol I was originally used by André-Marie Ampère, which originates from the French phrase intensité du courant, or current intensity, after whom the unit of electric current is named. There are many ways in which current can flow depending on the power source and generation of current. Looking at a graph, it is easy to visualize how current is flowing. On this graph, the absolute value of amplitude is the total voltage, while its direction moving positive or negative on the y-axis is its flow while moving through time, represented by the x-axis. In this video, we will be focusing on two of these currents, direct current and alternating current, two of the more common currents in use today. One of the earliest studies on current was in the 1700s when Benjamin Franklin and others were doing their experiments with direct current. At the time, very little was known about the mysterious force called electricity or flowing charges. Franklin had a convention of assigning positive charge signs to the things that were moving in the circuit and doing work. It turns out that Franklin was wrong, at least about the sign of the charges that move. Later, a physicist named Joseph Thomson performed an experiment that isolated these charges. He found that they were moving in the opposite direction of conventional current, the convention that Franklin surmised earlier. Also, we now know that the electrons are the charges free to move and the positive protons are not. This history led us to two different theories on how and in which direction these electrons flow. Conventional current flow or electron flow theory. Conventional current flow is one of the most often used. It states that electrons flow from positive to negative. In this demonstration, we can see the current moving from the positive terminal of the battery through the load to the negative terminal of the battery. Alternatively, electron flow is simply the opposite of conventional current flow. Current flows from the negative side of the battery through the load to the positive side, rather than vice versa. In this demonstration, we can see the current moving from the negative terminal of the battery through the load to the positive terminal of the battery. The truth is that electron flow theory is technically correct. We now know that current flows from the negative to the positive in conductors. So, why do we still mostly use conventional current flow if it's wrong? Well, it turns out that it doesn't really matter which convention you use if you're consistent. Since electrons and protons have equal but opposite charge, an electron flowing in one direction is equal to a proton flowing in the opposite direction. Therefore, we can still use conventional current flow even though it's technically wrong and come up with the right answer. In fact, most formulas used in electronics, such as Ohm's law, pretend that current flows from the positive to negative. That said, current in a wire or a circuit can still flow in either of two directions, depending on what the power source is and how it is attached to our circuit. Because of this, when defining current on a circuit, the direction representing positive current must be specified, usually by an arrow on the circuit schematic diagram. This is called the reference direction of current. When analyzing electrical circuits, the actual direction of current through a specific circuit is usually unknown until the analysis is complete. Consequently, the reference direction of currents are often assigned arbitrarily, usually following conventional current flow. When the circuit is solved, a negative value for the current implies the actual direction of current through the circuit that is opposite of the chosen reference direction. Moving on, another type of current flow is alternating current. Unlike direct current, where the electrons flow in one way or another, depending on what convention you're following, alternating current moves in both directions. This can be easily seen referring to our graph of currents. Alternating current describes the flow of charge that changes direction periodically. As a result, the voltage level also reverses along with the current, which is why we see a line that represents a sine wave having a positive and negative amplitude. Alternating current has to be kept at a stable frequency and amplitude to ensure stable power delivery. This is what a traditional incandescent light bulb looks like in slow motion while using alternating current. Note how the filament is flickering. That is the variable voltage that happens with AC. This is because, according to the graph, for a brief moment, voltage is actually at zero. Remember, current is the flow of electric charge, which means that the electrons need to be moving. When the electrons switch direction and head the other way, it passes its origin location and therefore hasn't moved. Usually this happens so fast that the human eye never notices. The same thing happens with all the things that run off alternating current, but we never notice because the devices never turn off long enough before they turn back on. We cannot have a video on electric current without covering the current wars between Thomas Edison and Nikola Tesla. With the invention of the electric light bulb, America raced to build the infrastructure to send power to the homes and businesses to power it and other early electric devices. There are many types of current, but when the United States was accepting bills to build their electric grid, there were two frontrunners: direct current, pioneered by Thomas Edison, and alternating current, pioneered by Nikola Tesla and funded by George Westinghouse. In the late 1800s, direct current could not easily be converted to high voltages. As a result, Edison proposed a small system of local power plants that would power individual neighborhoods or city sections. Power plants would need to be located within 1 mile of the end user. This limitation meant that you would need a small power plant at the end of every city street, and this made power distribution in rural areas extremely difficult, if not impossible. With Tesla's patents, Westinghouse worked to perfect the alternating current distribution system. Transformers provided an inexpensive method to step up the voltage of alternating current to several thousands of volts and then back down to usable levels. We needed to do this because at higher voltages, the same power could be transmitted at a much lower current, which meant less power loss due to resistance in the wires. Also, too high of current in a long transmission line will also result in the power lines heating up and melting at some point. This is why alternating current made perfect sense, which allowed for large power plants far away from communities with high voltage transmission lines dispersing into homes and businesses. As a result, large power plants could be located many miles away and serve a great number of people and buildings. In the end, we can see that alternating current won this war, and the United States electrical grids are built to support this. However, this was not the end for direct current. With modern technology, we are seeing a direct current renaissance. We now see direct current in all of our portable electronics and modern personal home grids with the use of solar panels. The phone and laptop you may be watching this video on is powered by direct current. Whether the flow of current is moving from positive to negative, negative to positive, or in both directions, we still need current for everyday modern life. Remember to like and subscribe if you liked this video, and thank you for watching.